Thanks, Ajith, for inviting in this very nice meeting. Yeah, this one. And congratulations, Bala, on reaching a very important milestone in life, and in our lives also. I also realized that in August 2009, we had the most important meeting where Indigo Consortium was formed. So that marks it, the 10 years of Indigo as well, this way. So I hope this marks the beginning, as we say in gravitational astronomy, beginning of your journey into the space-based detectors. Okay, let us, so I'll talk about the stochastic gravitational wave. It is supposed to be mostly on analysis, but since we did not have a session on the stochastic sources, so I'll also tell you some of the motivations that why we want to do this. And before you leave the hall, because it is stochastic, I'll tell you that stochastic is the future, okay, and more on that later. Okay, so stochastic gravitational backgrounds can be generated by different sources which are unresolved. That is, they're distant sources which cannot be resolved because our detectors have not reached enough sensitivity. So there are two kinds, popcorn and continuous. Popcorn is like one or the other CBCs are going on in, let's say, localized cluster. So it is a discontinuous signal with a duty cycle. So one happening, another happening, so there is a gap and so on. But then there is a continuous kind also, where, let's say, you consider a localized place like a cluster of galaxies, and there are 10 to the 8 millisecond pulsars or millisecond pulsars. Each one of them will have a line, which is like a forest of lines. We don't know where exactly each line falls, but then it creates a envelope. So these are the two kinds, and probably we should have slightly different strategies for each one of them, and people are working on those. So the main motivation for the stochastic search is that it may carry information which is not accessible in electromagnetic astronomy, as well as the binary searches which we do. Okay, I'll come to that in a moment. And it may also give us information on the anisotropic local universe. There is a lot of work going on there, even though we don't know exactly how much sensitivity we can get there. And of course, historically, the stochastic search was motivated by the primordial stochastic background, which is produced in the very early universe, including, and inflation is one of the biggest candidates. And also, stochastic searches can detect unknown persistent signals, which is one of the motivations. So since my talk had unknown, I'll just tell you what are the unknowns. So there are different kinds. For example, for the binaries, we know that those sources are there, but we don't know their distribution in redshift, for example. So stochastic searches can tell us something about that. Then there are sort of known unknowns that we know the primordial background is there, and at some point we have to detect it. But then we don't know exactly which model would be the right model, and so on. And then there are unknown unknowns. So this is one of the most interesting things that in any astronomy, any new field of astronomy, although we write proposals for the sources which are guaranteed, the excitement still lies in the unknown ones. And stochastic gives a very good way to see if there is a persistent unknown sources. Archana already talked about sources which can be burst sources and unknown, which we may be able to detect it in the burst searches, but stochastic gives you the way to say see unknown persistent sources. Okay, so basically, even if we don't detect, we would be able to probe all these kinds of sources and put strong constraints. For example, one can perform a stochastic search, get some results, combine that with the binary populations which have been detected, and put more constraints on the binary population. Okay, so some definitions which will be used, which is very common, and then I'll just tell you what it is. So generally, the term which is used is this omega GW of F, which is different from omega GW and so on. But you just consider this as the energy density per unit logarithmic frequency in the units of the critical density needed to close the universe. This term comes many times in the plot, so I should describe this. And then there is, for the anisotropic searches, there is some quantity called this P of omega, which basically shows how the power is distributed in the sky, which can be related to the specific intensity. But just, these are not very important, but just to, so that you are not lost. Now, since the background is stochastic, we cannot do matched filtering because we only know the power distribution, but not the phase. So the best way, or the optimal way to detect is that if you have two detectors which are geographically separated so that they have uncorrelated noise, then we can correlate the signals from those detectors, and the signal part, the true gravity wave signal part will be correlated, and if we can adjust the phase accordingly, then we can get information out of that. So this is the idea. Basically, noise is uncorrelated, and then this correlation with some filters can give us some information about the stochastic source. So it is like one detector signals is other detector's template in a crude way. Now, you already saw this, so this is the current limit for the isotropic stochastic background from LIGO-Virgo analysis. So if the background is statistically isotropic, that is essentially the same power is coming from every direction, and we choose the filters accordingly, then we get these limits. Sriram showed this plot yesterday and explained the inflation part of it. Well, we are quite far away from detecting the signal from inflation in LIGO band. CMB is much closer there. So this is our current sensitivity. It is slightly better now. It is somewhere here. We don't have such a plot for O2 yet. This is the design sensitivity. When we reach advanced LIGO's design sensitivity, which Rana may say that will take infinite years, but here you see that we are touching this, whatever, magenta and the green lines, which are the basically predicted backgrounds from binary black hole and binary neutron stars. So here it already gets quite interesting. As you can see, we may be able to detect it soon, meaning in the astronomical timescale, maybe few years. Now, this is what we do routinely for many years in LIGO, that for different spectral indices, that is, if you assume the spectral shape of the background and do an analysis, for different indices, we put a upper limit, okay? So this 0 corresponds to the slow roll inflation, this 2/3 corresponds to the backgrounds produced by the binaries, and this 3 corresponds to those sources like, millisecond pulsars and so on. Now, one could ask that if we believe that all these kind of sources exist, then why we should better do a joint analysis, which we proposed at some point, that we should produce plots like this as we do in cosmology, that there are these omega, that is the amplitude of the background, or this spectral index, and for omega 3, omega 2/3, omega 0, and so on. This is showing only 2, but we can make it bigger. So, and we did this, and then right now it is being pursued in the LIGO analysis. The results are currently public for the tensor scalar mode in this form, but we want to do it for different spectral indices. Anyway, I'll come to this little later, that why it is important to separate different backgrounds. Now, what are the expectations? These are the estimates for stochastic gravitational backgrounds after GW17, OH17, that is for binary neutron stars and binary black holes, and this blue line shows the total background expected. And so you focus on this one. I think this will be more interesting. So if you see, this is the observation time in months. This is O1, O2, and so on. And this blue one is the expected stochastic background from all the binaries in the fiducial model. There is a pretty big error bar, as you can see. And these lines show the significance at which we can make a detection, claim a detection. So this is 1 sigma, 3 sigma, 5 sigma. Now if you see that for a 3 sigma detection, we have to wait about 36 months, which is like 3 years, okay? Which is not a long time. Very soon it will come. And I believe that when we detect a stochastic background with the ground-based laser interferometric detector, it is going to be a quite a significant discovery, and it is not too far away. Okay, Now moving on, what we can learn, what science we can get out of these backgrounds. As you can see that because of the lack of number of sources right now, the number of detections in binary, there is quite a bit of uncertainty in the rate estimation, and we have quite a bit of uncertainty in understanding how these sources actually, these binaries actually formed. And this was after GW 1509 14. These kind of plots were made that for different astrophysical models which are possible, there is a very wide possibilities in the stochastic background. Okay? So this is actually a pretty good thing, that by measurement, through the measurement of stochastic background, the degeneracy can in principle be broken, okay, between different models. Of course, there is a very large error bar on top of that, and you might think that, okay, everything fits within the error bar, then how do we account for that? But this error bar is going to shrink as we detect more and more binaries. So I think that stochastic background detection will give a very important role in the rate estimation and finding out the models or a mix of it, which are creating the binaries. Okay, so why the stochastic part is complementing in a very nice way with the binary detections, individual binary detections. Now you see that this is a very nice plot made by Duncan Mitchell. See, this is redshift. These blue lines are for binary neutron stars, okay, the horizon for binary neutron stars. The red one is for binary black hole horizon. But most of the sources, the binaries, are here at higher redshifts. So by detecting the individual binaries, we are restricting to this very small region of the universe. Okay, this goes as actually cube of the universe, cube of the redshift essentially. So by doing a stochastic search, we are getting information which is coming from this huge part of the universe and the distant part. And this is what is very important, at least in the near term. The thing is that if you look at this plot, these are showing all the binaries in the universe, like sort of, these are models, these are cartoons, but then this tells the story very nicely. So this is O2, this is our horizon for neutron star and black hole binaries. With A plus also, we will stay in this region, okay? This is not really the happening place in the universe. With A plus, we will go slightly in the black hole regime, that is true, but okay, we don't know exactly when we are going to reach this sensitivity. The thing is that with Cosmic Explorer, we would be able to get all the binaries. At that point, the importance of detecting a stochastic background from binaries will become less important. But that is 2035. That there is more than 15 years remaining there. So it would be important that we get something in the next 5 to 7 years about this distribution in the universe. Okay, moving on. So these are, so far we have been talking only about binaries, but there are other sources in the universe, as I said. And if you look at these plots, these are for the stochastic background predicted from, let's say, millisecond pulsars, etc. So there are many other kinds of sources which are obviously there in the universe, and hopefully the gravitational-wave astronomy will shine light on them. So this is one of those plots which were made by Sanjeev and his collaborator, that if you consider the Virgo cluster and consider all the millisecond pulsars in the Virgo cluster and consider a slightly higher eccentricity, let's say 10 to the minus 5, the thing is that it does create a hotspot in the stochastic background, okay? Now, whether the current detectors will really be able to detect it or not is not the important thing, but one thing is for sure, that with a directed, targeted search, if there is a bright spot on the sky, as compared to the isotropic background, which is integrated over much larger redshift, we will be able to detect the contrast. It is like Olber's paradox, but put in the context of gravitational-wave detectors which has narrow frequency bands. So this we showed at some point, but I'm not getting into the details there. Now what we did recently is that you take to see whether we will be able to probe the anisotropy of the nearby universe with using these millisecond pulsars as kind of tracers. Okay, so suppose you take the galaxy catalog. This is a great catalog which one of the students, Dipali Agarwal, took, and then she translated all the galaxies by basically you take the blue luminosity, divide by the distance, and translate to some kind of stochastic background, the maximum stochastic background that you can detect, and you get a plot like this. You can clearly see that the anisotropy is kind of captured here. The thing is that you get this plot is actually integrated over all the detectors, advanced LIGO, A+, then I'm not sure, Voyager 3-year, then Cosmic Explorer 3-year, all those things if you do, if you take 10 to the minus 5 eccentricity, then you reach a SNR of like 4,000. But this is just to exaggerate this. The thing is that SNR goes as as eccentricity square. So if you have 10 to the minus 6, this falls by factor of 100. And if it is 10 to the minus 7, then actually we go to SNR of like 0.3 or something. So with this current method, in this kind of setting, it will be very difficult to probe the anisotropies, but then we are also exploring other algorithms if we can get something more out of it. Okay, moving on. So so how do we make a map? We understand that the anisotropy is present. How do we make a map? That is done using a radiometer algorithm. I think most of you have seen it at somewhere. It is like Earth rotation synthesis imaging used in radio astronomy. If you have two detectors and you want to map measure the power of the background that is coming from a direction, let's say omega, then you adjust for the phase delay and keep integrating, and then you can get the power in that direction. And then for every direction, if you do this analysis, you can make a map. And LIGO Fargo collaboration has been producing such maps for a while. These are basically, if you do this perform this analysis, you get some kind of SNR, and then you put kind of upper limit on the maps. Okay, so this is what we do. Now, the thing is that this analysis used to take quite a bit of time, and then this was limited to the broadband analysis only. So we could not make maps at every frequency. Now there is something which we came up with. It's called the algorithm for folding, that you take the whole year's data and you can actually compress it to only one sidereal day's data without any loss of accuracy. Okay, so this is absolutely a mathematical identity. On top of that, we did something called the PyStoch that took advantage of this small compressed data, and the way you can do the computation with some other smart algorithms and symmetries, etc. So this made the algorithm actually a few thousand times faster. So what happens is that now one can do this kind of analysis on a laptop. Okay, so people, if they have their favorite model, they can do it this way. So the advantage, as I said, is that you can do narrowband maps. So now we were able to, with this compressed data set, we were able to make a map at every individual frequency. Okay, so this is quite interesting. Now, why are we interested in this kind of foreground studies? The thing is that, you see, ultimately, we want to detect the stochastic background from the early universe. But if you see the frequency, these are the predicted stochastic background from many different sources. And you see the whole frequency band, except for maybe small windows, is filled with different foregrounds. Okay, if we do not understand this foreground very well, I think it will be very difficult to claim a detection of the primordial background. This would be very similar to what happened with BICEP. You detect something and you would not know what we have detected. So which is why I think we should really focus on every band and try to develop a full understanding of what sources are there in which band. For example, if you see the pulsar timing array, which is supposed to come close to detecting the primordial background, has already some massive binary background predicted. Okay, so these things will have to be sorted out, right? But of course, this is a bit future, but then this is the future of gravitational astronomy, so we can think about it. I'll also show one of the things we did to find the stochastic background from all the extrasolar planets. Even though each individual planet contributes very little, when you add all of them, you get a background which is not insignificant, okay? And this is the background predicted from our galaxy, the yellow one is from our galaxy, and this one is with the rest of the universe and so on. This is LISA's sensitivity curve. It is 2 orders of magnitude below that, but on the other hand, LISA Pathfinder is already 1 order of magnitude better than the design sensitivity for LISA. So, you know, in the near future, well, in 10 years or before I reach 65, let's say, things can happen. So, okay, so and this was done, by the way, with by Shilpa, who is sitting in that corner there. Okay, so I will stop here. That the whole frequency band in gravitational waves is actually full of different sources. Right now, we are detecting only some of the sources whose phases are well modeled. But then the frequency axis is full of sources whose phases are not well modeled, and different detectors in different bands are being proposed. So I think the future is pretty interesting. Stop here.
Questions? Yeah.
Yeah, so you showed this spectral index, right? So how sensitive is that for the astrophysical mass distribution, spin distributions, etc.?
The thing is that the spectral index is almost remains the same. That if, so basically that the spectral index is 2/3 for the binaries. It essentially remains the same except for the last part. So you know, what happens in that way is that when you have multiple sources which have very similar spectral indices, you will be able to search as a clubbed combined background. It will be very difficult to resolve them individually. That means resolving the neutron star and binary black holes will not be a very easy task. But even then, that information will be useful, right? Because you will know the split between neutron star binaries and binary black holes from the regular detections, from the individual detections.
Yeah, Chris. Yeah.
Hi. I've got a bunch of questions. I'll let other people ask them. Yeah. But you made this argument about when you get down to the stochastic background, the astrophysical stochastic background of the binary neutron stars, binary black holes, that would then inform rates, right?
Yeah,
you would look, but aren't you going to get that information from all the actual detections that you make in O3, sorry? Aren't you going to get that information from all the individual detections of these events that we get?
Correct, in the local universe.
Because as you move up that plot of sensitivity, you'll actually be detecting the local ones and getting our rates error down and down, so that will tell you when you're going to actually find the stochastic background.
That is true, that when we have, let's say, 1,000 detections, then the rate calculation, the error bar will be small, but it is, I think, small for each one of the models. So there will be small error bars for each one of the models. So that curve which I showed, you know, with a big error bar will be probably split into multiple plots. That is what I expect. You understand what I'm saying? No.
I understand. I don't necessarily agree. Maybe.
Well, wait, this one. See, this one are for different models, right? So each one of them will have a small error bars. So this is, right now we are showing only the fiducial model error bar, because otherwise this plot will look a big mess, right? I mean, you have error bar for each one of the models, right? This is a Poisson error bar.
But your pink error bar there is the Poisson error from the rates, right, that we have already.
Well, for a given, but you are putting in the model also there. Consider just the fiducial model and the rates you have got. Each one correspond to the same rate here. Each of these models is just that the astrophysics has been changed.
Oh, okay.
So as you go back in time, it's meaning in redshift, each one have a.
I get it.
Okay, what else?
So when you are talking about detecting the anisotropy, you discussed quite a bit about sensitivity to what the eccentricity is. But your simulation right now is driven by the Glade map, which is no, horrendously incomplete. There is a full gap in the galactic plane, and essentially it is tracing parts of the sky where SDS has decided to take images.
That is true. But then we can either try to extrapolate it, that is one way to do it, But even then, those details will come into the picture. Suppose there was one part of the sky which was really well sampled, okay? Then we would be able to predict the background from that part very well, right? But the problem is that the eccentricity is so small that, it is not coming to a point when the completeness is going to be the...
So my question was different. My question was that if the sky is not this inhomogeneous, okay, even for eccentricities of 10 raised to -5, will this effect still be detectable?
You mean that if the eccentricities are small?
No, eccentricity is good. You take -5, -4, whatever. But the sky is more uniform because it probably is.
It will be detected. That work I did not show. That me, Sanjeev, and Noidita, we actually did a work to show. Suppose there is you take a cluster of galaxies. Okay, you have multiple clusters of galaxies, right? When you take, let's say, Virgo cluster and the rest of the universe, Virgo cluster does stand out by factor of quite significantly. It depends on, but the thing is that it depends on how far the sources are. If the sources are localized in the sense of that the maximum is at around the redshift of 2 or 3, then you are able to resolve the Virgo cluster. If it is beyond redshift of 3, that means they are really like up to redshift of 6 or 7, which is unlikely for millisecond pulsars, then it is unlikely to, then we won't be able to resolve it. Then it will be dominated by the stochastic background.
Sugat, yeah.
Okay, so a comment and a question. The comment is on precisely this slide. There was a work that like Eric Thrane, Dipankar Talukdarai, and Tanya Rejambu did, where we in fact implemented this method in 2014 to show that for like galactic neutron star distributions as gravitars, the ellipticity, so E is actually the ellipticity of a neutron star. It's bounded to be like less than 10 to the -7. With advanced LIGO, we projected that it would be bounded to less than 10 to the -8, assuming that we don't actually detect a signal.
That is right. So this is, we excluded the galactic binaries. This is not for the galactic neutron stars. This is the extragalactic one.
Yeah, but if the neutron stars are the same, but if the neutron stars are the same, then the galactic population will put.
That is right. So that's what I'm saying. Basically, the bottom line is that with this kind of eccentricity or ellipticities, it is going to be difficult with the current algorithm, existing algorithms, to detect these sources. We are also considering, we are exploring that if there is some other routes through which we can extract more SNRs, because we can do more focused searches. These are kind of broadband.
Okay, quick question is, in all of these, the main problem is going to be Schumann resonances. In fact, they're almost rearing their head even with the O2, isotropic search.
Yeah.
What is being done to tackle that?
Well, Schumann resonances right now, I think it is, right now it is not affecting our SNR. But we have to see actually exactly, so there are measurements are being done, people are working on it. So Schumann resonances are not going to affect these ones. These are very high frequency.
Yeah. So they affect the lower frequencies for isotropic searches.
Isotropic searches, it will matter. But I think, so first of all, they are burst kind. If we can suppose we get a catalog that, okay, what are the times when Schumann resonances were more, we can probably excise the data at that point. But that is a different discussion. I am not also exactly involved in that. So I don't know exactly what is going on right now. But as far as I know, that this is going to affect when the sensitivity is more. We are not yet limited by that. And the other thing is that we should be able to remove the data of certain parts, period.
So let's thank Sanjit for a very nice talk. And if anybody has one question for any of the three speakers, I can allow that now. You have one, you can ask.
Right, so it was related to this. This is one of my questions from before. It's a nice link between, so using the GLADE catalog, we use that for the cosmology, for the Hubble constant measurement, and we have to address this issue that Arun brought up, that is completely selection bias affected. But we have techniques to address that, if that is useful.
Oh, that will be very useful to make this plot much better.
Yeah. And the other thing is that the continuous wave search, the group for the known pulsars has started doing inference on the ellipticity distribution of all of the pulsars, and so you could put a distribution for epsilon rather than fixed values if you
Okay, I did not address this, but this is one of the, since there was limited time, but this is very interesting, that why the analysis groups are more interested in this kind of searches. Okay, I'll just, since you brought this up, I'll just describe this. So if we produce, let's say, narrowband maps at each frequency, and we come up with, this is Gaussian noise, but if we come up with algorithms which will basically pick bright spots on the sky, continuous wave group, which cannot do an optimal all-sky narrowband search right now, can focus in those frequencies, in those directions in the sky to do a higher resolution search there. With, and the maps we showed with the GLED catalog, that can act as a prior, that we will see even, see, the thing is that there will be many bright spots here, for example, like this and this, which will be clearly by knowledge. Oh, well, yeah. So this, we can discuss this more later on. Okay.
So I had just one comment actually. This is regarding about the first talk actually. Regarding this thing about machine learning part of it, and there are some algorithms based on machine learning. But nowadays I find that in the corporate sector, you have to explain the machine, what the machine does. So maybe that's the point. I mean that you may have algorithm, but nobody else understands except you. So then you have to explain that what it is doing. I think that's what is missing. Maybe if that is done, then they might get accepted or what, I don't know.
That was done for, I should advertise Nikhil's work here, which he applied machine learning in a very nice way, which was very well appreciated in LIGO's commissioning team. Yeah. So what was happening was that, so suppose something goes wrong in the detector. Suppose the detector is not locked. Suppose the detector is not locked. Yeah. How would you figure out the cause and how do you bring it back? Yeah. So people used to ask the operators and the engineers that what could have gone wrong, what could have gone, and so on. So Nikhil put all this information in machine learning so that when something goes wrong, it would automatically figure out what might be the cause and then plot those channels and plot the relevant logs, which were used to answer this question. And this was pretty heavily used in the control rooms in LIGO.
Maybe this is one of the things. Okay, so let us close the session because we are quite running a bit late. So let's clap for all the speakers.